Hello and welcome to the final video of radians for this series of Reigate College's post-Easter work for mathematics. So what we're going to be looking at today are these things called small angle approximations. So what these are is what happens to sine theta, for instance, or cos theta or tan theta, as theta gets closer and closer to zero. A lot of students ask me, what is small? What do you mean by small? That's hard to quantify. A small angle is small, okay? In degrees, we're talking, small would probably be around 5 or fewer degrees. In radians, remember, one degree is pi over 180 radians. So 5 degrees, for instance, is going to be 5 pi over 180, which is 0.0873. This is a very small number. This is a much, much smaller number than 5. So this is something you really have to be wary of when doing these small angle approximations. You must work in radians. If you are working in degrees, this does not work. Okay? So much so that this was actually a question on the exam in 2019. Was a student does all the small angle approximation stuff that we're going to look at in this video, but did the whole thing in radians. And the question was, why is the student wrong? And this was the only thing that they did incorrectly, was they were working in degrees, not radians. So you must work in radians. So what we're going to do is we're going to use the graphs to have a look at what happens when theta, or in this case x, because that's what I'm drawing on, gets very, very small. We can see here I've plotted y equals sine x. For x is between minus pi over 2 and 2 pi. As we've established, these are not small angles. So let's change our axis so we have relatively small numbers. So this is a very, very small graph, as you can see. Let's change that so it's a slightly more sensible unit, and let's change this so it's a slightly more sensible unit. Oops. Let's do that. Okay. So let's have a look at this graph. What does this graph kind of look like? Now the thing to remember, you can see there's still a slight curve. But what does this look like? Maybe hard to spot. Let's try zooming in a little bit more. So let's go 0.05 to 0.05. Let's go 0.1. Actually, no, that's not going to be helpful. It might be to 0.1. And we'll make our step 0.01. Does this make it a little clearer? Some of you will already be able to spot what this graph looks like, but let's have a look. This looks like a straight line, and we can see here that when x is really small, sine x, or the y coordinate, is the same. we can see here at 0.02, whoops, that's the same, and 0.03, where are we? There we go. It's still the same. So this looks like y equals x, and you can see when we zoom in very, very far, it looks like that the graph of y equals x fits exactly over y equals sine x. There will be some deviation, but when x is small, or when theta is small, sine theta is approximately equal to theta. And again, we can see that from the graph here. So let's get rid of that one, and let's put cos x in there. Now cos x is going to be a little different. I'm going to have to rechange my axes, so bear with me, okay, because it doesn't show up there. So let's change our y-axis, which is the only one that matters, to 0.9. Oh, no, I just want minus 0 to 0.9 to 1.1. Oops. Or 1.2. Now that's not hugely helpful because my x-axis is very, very small. So let's change that to minus 0.1 to 0.1. Now we can see that there's a curve here. You might think, oh, this is very similar to y equals 1. But remember, this is a small angle approximation. My x-axis is still some really small numbers. It doesn't work over here. This is close to 1 on the y-axis, but it isn't equal to 1. So this is not a bad approximation, but it's not a good approximation. If I zoom out with the x-axis a little more, hopefully things should become a little clearer. So x is 0.5, still a very small number. But what does this look like now? This looks like a quadratic. More specifically, a negative quadratic. So let's think about the graph of y equals, well, let's first off think about x squared. Now we can see this graph doesn't appear on my screen. It's nowhere near this one. Why is that? Well, because x squared goes through the x-axis, or goes through the origin. So we need to make this go through 1. How do we do that? We translate it 1 unit upwards. Okay, we can also see this is the wrong way up. How do we change that? Stick a minus on the front. Now, this is close. You can see we've got the shape right, but it doesn't fit on the graph as well as y equals x did on sine. So that's an issue. But these look very, very similar. This blue one, so cos x, looks less steep than the red one, which was our guess at the approximation. So how can we make this one less steep? Well, what we can do is make this a fraction. And we can see here that this is a much better approximation for our cos x graph. So that's going to be our next approximation. Oops. That cos x, when theta is small, cos theta is approximately equal to 1 minus theta squared over 2. Last one we need to look at is tan x. So let's just very quickly blast through that now. Oops. There we go. So again, if we zoom in, we can see we get a very, very similar looking graph to sine x. So we can put this one over the top as well. So it looks like that when theta is small, tan theta is approximately theta. Okay? These are the 3 small angle approximations, and they are in the formula book. You do not need to learn them. What you do need to be able to do, however, is use them. So, let's have a look at page 18 in your workbook. When theta is small, find the approximate values of part A, sine 2 theta plus tan theta over 2 theta. So, we know our small angle approximations. When tan is small, this is theta. But what happens with sine 2 theta? So let's go back to our graphs just to have a quick look at that. Let's put that one in. So we know that sine x is really close to y equals x. But what happens if we stick a 2 in it? Well, this purple graph here, this is y equals x. The red one is sine x, or sine 2x. Trying to get as close as I can. We can see, there we go, that x is 0.005 and y is 0.01. So how do we think that changes it? So the thing with the small angle approximations is if you have 2 theta, or if you have any number inside the trig function, that just replaces the number or the theta in the trig identity, or in the small angle approximation. So this is approximately equal to, so sine theta is approximately theta, so sine 2 theta is approximately 2 theta. Tan theta, we know is theta, and 2 theta, well, 2 theta stays as 2 theta. Okay? Which simplifies very nicely to 3 over 2. And we can test that. We can check it in our calculator. So we think when theta's really small, we're going to get 3 over 2. So let's choose a really small value of theta. So sine of 2 times 0.05, for instance, very small value, plus tan of 0.05, over 2 times 0.05. We can see this is very close to 3 over 2. This is very close to 1.5. If we make theta even smaller, we can see we get even closer. So this is pretty good. This is a pretty close approximation when theta is small. So let's look at number 2, or part B. Cos of 4 theta minus 1 over theta sine 2 theta. So this one we need to be careful because cos theta has a squared in it. So this is approximately equal to, so cos 4 theta okay, so remember, the 4 theta, the thing that's inside the trig, goes where the theta is. So the whole thing must be squared. Note this is not that. It's not 4 theta squared. So be careful with that. Now we know that sine 2 theta, we've already seen, is approximately 2 theta. So this is approximately minus 16 over 2, 8 theta squared over 2 theta squared. So this is approximately minus 4. And again, we can check it. So cos of 4 times 0.01 minus 1 over 0.01 times 2 times 0.01. We see very close to minus 4. Now, just something to pay attention to, it's not on this page of the workbook, but something that the exam would like to do a lot is worry about things like cos squared theta. Now, when this is small, it's approximately equal to that. You've got to make sure if this comes up, you've got to make sure that you are expanding these brackets correctly. Now, if you use your binomial expansion, you should be able to do that no problem. If you can't, maybe multiply out the brackets using FOIL or the pelican or the smiley face or whichever way you like to do that. But this expands to 1 minus theta squared plus theta squared over 4. Okay, oops, theta to the 4 over 4. The thing to pay attention to, particularly with this type of question, is theta is very small. Which means that theta to the 4 is basically 0. So you need to show use of it, but also recognize that most likely you're going to end up ignoring it. And using something like that. Okay, so pay attention to that. So one more exercise for you to be working on for radians. This is a relatively short exercise, so I want you to do the whole thing. This is exercise 5F on page 134. Okay. If you want a particularly challenging question, then have a look at the challenge box on page 135. Okay, that is quite a tricky question, but quite nice and gives you a little bit of problem-solving type stuff. So that's it for this week. That's all of radians. What we'll be looking at next week is looking at something called algebraic methods, which links a little bit with stuff you've already done this year, and a new version of proof, which also involves 2 proofs that you have to learn the methods for, almost word for word. Okay, so that's something to look forward to next week. Thank you for watching. Goodbye.